I think we got most of the people that wanted to sitting, so that's good. So we're going to continue the day with a second panel, and I would like to introduce Professor Freud from the Sloan, who is going to be managing and moderating this wonderful panel. And I will let Rob introduce the panel.
Thank you very much. Nice to see you all this afternoon. And actually, there are a couple people who were here in the morning that I didn't even think were here in the morning, including my own former student, Andy's son. So the other panelists are Cindy Barnhart, Professor Cindy Barnhart, Professor John Tsitsiklis, and Professor Dick Larson. Our topic is OR at MIT. But you know what, I'm just kind of want to take this thing out. Let's do some rap dancing or something. So, no, I just want to just kind of, I wanted to just kind of loosen things up a little, even though they were sufficiently loosened this morning, before I get into a convergence proof that I want to show everyone. So who was not here this morning, who is here now? So just, okay, so I see, wait, Rob, you weren't here this morning? Oh, okay, all right. All right, now it all is beginning to make sense. All right, let me ask you something. Who's now back at the ORC for the first time since graduating? Okay, so just a few. All right, that's good. So you just graduated, right? Yeah, okay, all right. So, and Andy, you didn't raise your hand, but, oh, that's right. Okay, that's right. All right. And then who's back for like the second time or third time? You know, okay, so I see. Wow. All right. Very interesting. And then I have another question. So who has kept in touch with his or her advisor? Okay. Those of you that didn't raise your hands now. Okay. All right. Some of you were grateful for this. No, I have no point. I just try to loosen things up. That's right. Okay.
Start your dancing.
So I have, well, first I just have a personal thing to say, but I already said it to him already, but I'll say it in front of everyone else, which is, so this is my 28th year here and at MIT, which is a little mind-blowing, but so at least one person here was in the very first course that I taught here, which was Tony Cox, who's sitting in the front row. And when I saw Tony, it almost sort of brought tears to my eyes. So it was just, that's really nice. It's just, and then I have some anecdotes in no particular order. So one is about some of the stuff that was discussed this morning, okay? And I don't know if some of you were at the OR Center's 50th celebration. I think it was in 2003 or 2004, okay? And where is Mitchell Berman? There he is. All right, so, you know, Mitchell told an anecdote there. And this is a true story, okay? This is unedited, okay? And it involves my wife, actually. So, and that center, no, because, so watch this. So my wife has an undergraduate degree in industrial engineering, all right, from the University of Michigan, and she got an MBA with a specialization in manufacturing, actually Michigan's LFM program, which is called the Tauber something or other, okay. So, and she's born and bred and raised in Michigan, sort of car culture, okay. So I go to the ORC thing, and Mitchell gave a very provocative talk, I believe, then, and you cited an anecdote by Alex Trotman, who was the CEO of Ford, who was also your father-in-law, right? Okay, at the time. All right, so, I mean, I'm sure he's still your father-in-law, but so, you know, if you think about this, though, there was quite, because Mitchell was very challenging in the anecdote, because he said something to the effect that, you know, when he was introduced to his father-in-law, and you know, I guess Alex said to him, you know, what do you do? And I run this company, you know, an OR company, and he said, what's OR? Okay, and Mitchell said, OR is in trouble if the CEO of Ford doesn't know what OR is, all right? So just now, okay. I went home that night, and I mentioned this to my wife. And the first thing she said from that, she said, no, he's got it all wrong. Ford's in trouble if the CEO of Ford doesn't know what OR is. Okay, so I really, okay, all right? And
Can you tell everybody who the current CEO of Ford is?
I can only tell a couple of you.
He was my student.
What?
He was my student.
Oh, is that right?
Yeah.
Oh, okay. And
So I presume he knows what OR is.
what's his name?
Ellen Llewellyn.
Alan Mullally?
Llewellyn.
Okay, all right. So, and Ford's doing pretty good these days, I believe. Good. Okay. All right. Okay. So, the other thing is, I just got to tell you because I'm feeling nostalgic because actually my wife is in Michigan this weekend. In fact, she is at the Michigan State football game right now. Okay. So, she and I were introduced, and but we talked on the phone, and then apparently she emailed a friend of hers who she had gone to college with, and said, you know, this guy is like a professor of linear programming or whatever. And then she emailed one of her friends who she took linear programming with from John Burge. Okay, and so the friend writes back to her regarding your linear programming inquiry, and all right. So that is, and then. But my last anecdote before we get down to the business at hand also has to do with this morning, and it's actually true. So I live out in Concord, Massachusetts, about 20 miles from here, a nice quiet suburb. And my wife and I joined what's called a gourmet club. Okay, so it's not what you think, actually. It's a way for couples to get to know other couples. It's like part of this newcomers organization or something. All right, so we're put into, and the way the gourmet club works is, it's 10 people, it's 5 couples, and then you have a meal at each person's house. It's supposed to be a fancy meal every 2 months. You know, it's at a different person's house. And so this group of, they had been 10, and then this couple moved away, and then we were their replacement. So they all knew one another, and they were all like, I wonder who these people are or whatever. And then there's this guy there named Tony, who, you know, he says, oh, so you're a professor at MIT. You know, what do you do? And I said, well, I'm really at the business school. And he goes, well, like, what kind of stuff do you do? And I go, well, it kind of has to do with making decisions. And he goes, well, like, is it quantitative? Or I said, well, it tends to be kind of quantitative. Well, like, you know, do you do, do you draw diagrams? And I go, well, I do some diagrams, maybe some mathematics. He goes, oh, it's mathematical decision-making, so it's not like strat. And we're doing this dance for like 15 or 20 minutes. And he goes, boy, it sounds like, he says, it sounds like maybe it's like systems analysis. And I go, well, it's kind of like that. He goes, or operations research. And I go, yes, it's operations research. And he goes, oh, you're an OR guy too. Okay, all right. So, how many of you use the software, the decision analysis software from DPL? Okay, so that's his software. All right, so I mean, he runs Syncopation. They have a booth at every Informs conference, and I'm anyway, that is that. Okay. Now we're going to talk about OR at MIT. All right, so our first panelist is Cindy Barnhart.
Okay, I'm almost afraid to start. Can you hear me? Good. All right, so I will talk a little bit about OR at MIT. I'm going to come at it from the perspective of where I sit at MIT, and that is in the School of Engineering. So I thought I would share a little bit with you about, I'll give you just 2 examples because we're supposed to keep this really short. One in one in research and one in education about things that we're doing in the School of Engineering that I think are especially related to OR at MIT. Okay, so first I'm going to share with you a slide from the current School of Engineering strategic plan. And after a bunch of exercises in strategic thinking, we sort of divided life at MIT into these 75-year buckets. And we said the first 75 years where there was a lot of focus on building infrastructure, the second building industry, and the next will be about building a better planet. So how does this relate to OR? I think that this mirrors kind of the, except maybe on a different time scale, what we do in OR as well. We've had a history of building our algorithms and our models, applying them in industry and government. And as we look to the future, I think many of us are motivated by the grand societal challenges out there that will contribute to building a better planet. Now, why I think this is really relevant to OR is that to build a better planet, it isn't about thinking in terms of these disciplinary buckets, and we've been talking about this morning. It really is about taking a multidisciplinary approach. So I said I'd give you two examples, one education and one research. So let me tell you about what's going on in education, a trend we see in the School of Engineering, and how it relates to OR. So I would say about 9 years ago, in mechanical engineering, they created an accredited degree, and they refer to it as the flexible or tailored engineering degree. So this engineering degree is, in mechanical engineering, has at its core mechanical engineering, but it provides the students the flexibility to design their own concentration, typically a multidisciplinary concentration that wraps around that core mechanical engineering discipline. What we have seen is that because of this interest among our students of building a better planet, they tend to have, some of them tend to have passion that's about making the world better. And so they don't necessarily just want to study the traditional mechanical or civil engineering. They want to take those disciplinary skills and combine with them skills to address energy and transportation and all sorts of other things. So if you look at the degree in mechanical engineering, over the last 3 years, it's our fastest growing degree in the school. Mechanical engineering is our fastest growing department in the school. And if you look at what these students are doing, I've just thrown up here, you see engineering management as the second most popular option that's 2009, that's 2008. And if you look at the trend, engineering management, which is like management science, OR, has been in the top 3 for the last 8 or 9 years in terms of the options. So what you see is these students who are interested in this multidisciplinary education recognize the importance of having the OR skill set. So although here at MIT we don't have an OR department, we don't have technically we don't have an IE department. What we do have, though, are many engineers who are coming out that now have a lot of exposure to OR. Okay, so let me come back to that at the end and switch now to research. So another thing that's going on at MIT is we have a new initiative, called Transportation at MIT, and it's exactly bringing you back to the grand societal challenge. This time it's about mobility and this great wave of mass mobility that's yet to come, a current transportation system that won't scale up to meet that challenge, and this desire to do something about it. So one of the things that we're doing here at MIT is a project jointly with Singapore. Patrick's been very involved with that, as has Amedeo Odoni. And in fact, 140 other people. That's how many people now are involved in this project. And what it's about is looking at what can you do to address urban mobility challenges. So I talk about this because I can show you this cute little picture. this cute little, oh, maybe I can't. Let's see if I can figure out how to do it. I know there's a way. Aha. Okay, so I'm showing you this because when we first started talking about the Singapore transportation project, Bill Mitchell, who was in architecture and the Media Lab, came and said, I have this wonderful city car concept. It is a little electric vehicle, and it's meant to help provide mobility for people in urban areas. It folds up like this and stacks like a shopping cart. And he had the idea that this could be part of a transportation system that enabled people to get where they are to where they want to go easily. So what we did was we pulled together a team to think about how urban mobility might look in the future. And we had already this kind of car concept in mind. And so I'm just going to really quickly tell you what this interdisciplinary, multidisciplinary team thought about when they thought about a future transportation system. So they said, okay, so we have a meeting at 9 o'clock we have to get to. And what we do is we have a system that in the background goes and figures out how we ought to get to that meeting. And the answer is the mobility on demand electric vehicle will pick you up at your office, bring you to the train station, you take the train to another station, you get off, there will be another mobility on demand electric vehicle, get you to your destination. So your phone reserves the vehicles for your first and last legs of the trip. At 8:05, it alerts you that you need to go down and start your travel. Your mobility on demand electric vehicle arrives autonomously and is ready outside your door when you get there. On the way to the rail station, there's an alert that in 200 meters, so you get this alert because the cars are talking to each other, and the alert says, the roadway surface is wet and slippery, slow down. Then you get another alert that says, real-time information from the rail station, there's a disturbance and a delay. It's no longer optimal for you to be going to that train station. So instead, it, in real time, traffic aware, reroutes you. And the new plan is you just stay in that little car and get to where you're going directly. So your mobility on demand electric vehicle reserved for the last leg is canceled. You arrive at your meeting on time. And then your electric vehicle repositions itself to where it should be needed next. So as you look at this vision of mobility, as I said, it started with someone from the Media Lab coming and saying, I have this vehicle. But the system, throughout that system, are all sorts of great OR questions. So all of us who are in OR immediately look at this and say, wow, there's so many interesting optimization questions to be formulated here and so many challenges. So the point of this is that this transportation example is just one of many. There's an energy initiative. There's an environment initiative. There's a Koch Cancer Center. The list can go on and on and on. And John will probably tell you about some of the other options that are opportunities that are being created in EECS. And there's, I think, throughout the Institute, a great opportunity for us in OR to contribute. So that brings me to my very last slide. And okay, so that doesn't look interesting, but hopefully it will in a second. So one of the big challenges that we find at MIT is that there are people across the Institute with whom you could collaborate on these multidisciplinary projects, but you don't know who they are. Even though I think someone was incredibly brilliant some 60 years ago when they designed the OR Center as the center that kind of reaches out and spans the Institute. Even with that structure, you don't know everybody. You can't find everyone. So we're in the process now of creating a system to help us do that. So it's not fully built, but this is what I can show you so far. So for example, hold on, let me put this one up. I typed in here transportation optimization, and we have a team of postdocs and faculty who are using OR techniques, and that actual NLP research group isn't nonlinear programming, it's natural language processing. And we have data miners and putting together, when you type in a query, looking at the public information at MIT, who's related to it and who has collaborated and published together. And this isn't showing the whole thing, but the idea is that it will allow us as we start. Here's Georgia. Bring her over here. You kind of see who she's connected to. And I'm sure you can recognize lots of the people here. The interesting thing is there are people you wouldn't recognize too. And those are the people that I think this tool is great because it allows you to reach out to other MIT colleagues who are doing something in the field that you might want to know about. And I'll stop there.
Thank you very much. John. John Jasiklis is the next panelist to speak.
So the subject is OR at MIT, but after Rob's introduction, it got my mind spinning about OR in the larger picture and OR and important people. So it reminded me of being at a dinner with a well-known Greek politician, and he asked me what exactly I was teaching and all that. And then he goes, "Oh, my father used to teach linear programming." So I was definitely impressed that the Greek politician knew about linear programming. So that tells you that there is some recognition about the field. Now, the sad part of the story is that this guy is now the prime minister, and the Greek and the Greek economy is not doing that great. But I don't think we'll blame it on OR for this. Okay, so just putting this title up there gets you into the existential issue of what do these symbols mean. So what's OR? What's happening in terms of OR at MIT? And I guess the first question is, so what exactly do we mean by OR? Okay, OR has to do with probability, optimization. These are the methodological tools, and something to do with applications. So it's these tools applied to doing useful things. So you take that definition, and then you realize that basically half of MIT is doing OR. So and there's not much to say about this. Okay, but maybe the rest of MIT might not agree completely with that picture. They'll say, no, some people will say half of MIT is doing applied mathematics, for example. So what's a little more special about OR, you can take the somewhat more narrow view and say, yes, it's probability optimization, but dealing with problems that have a certain flavor, which traditionally, of course, the word tells you, it has to do with operations and maybe service systems and all that. I think, at least my view, is that things are somewhere in the middle. It's a little broader than just service and operations, but anything that has to do with systems in which we want to allocate resources and with infrastructures that we design to put them in place to do something, and we ask the question of how to operate them. So even so, now it's still a pretty big chunk. I think anything that involves those three components basically qualifies as OR. Lots and lots of people do that, even if they don't know that they are doing OR. And now, how come not all of them identify themselves as OR people? I think here's the sociology that comes in. It has to do who happened to work with whom, what classes did you take, which societies do you find most comfortable in going to, and so on. So one can perhaps take an operational view that OR at MIT is happening by people who have some relation either with OR journals, OR conferences, and so on. So if you take that view, is there a lot of OR in that narrower view outside, let's say, outside this side of campus on the engineering side? Well, I live in that entity called LIDS, and I went there. It's a lab which sits within the School of Engineering. And I did a count, and it turns out that approximately half of the faculty who are in Leeds are also affiliated with the Operations Research Center. So there's really a continuum of activities. You can say that plenty of OR is also happening out there, and it's hard to distinguish one from the other. So what kind of activities are there? All these faculty are involved in many different topics. And here they are in alphabetical order, but these are some types of activities that are currently active, and I've probably missed a few. So I'm starting with the application domains. Anything to do with networks is traditional OR in a basic sense, although computer networks is a subject that's also had its own life in the EECS type of community. But fundamentally, many of the problems are one and the same. Energy is a big field these days. There's activity. How do you operate the smart grid in the new world that's going to be coming about? There's plenty of resource allocation, issues of pricing, gaming. How do you design a system of that kind? Now, healthcare, problems that have to do with healthcare, starting from the low level of biology going up to the level of delivering services. That's of interest, and there's some of that that's happening. Was then the subject of social networks. Does it belong to OR or not? I guess that's a philosophical issue, no need to get into it, but many of the tools and the methods and techniques that are used there definitely touch with traditional OR domains, and OR type of thinking has to contribute there. And of course, there's transportation, the activities that Cindy mentioned, and many, many others. Just so that we don't forget who we are, there's also some theory happening. So the application domains are definitely interesting. They are the ones who provide the inspiration for doing useful and interesting theories. But definitely one of our charges, at least the official mission of Leeds, is to develop novel analytical methodologies and apply them to physical or man-made systems. So the development of methodologies by themselves is a big part of what we do. So instead of trying to give more of big picture kind of thing, I will switch to the opposite end of the spectrum and just show you some very short vignettes about types of problems that one may encounter. And I'll go back to Tim's, who's here, PhD thesis. This is an application in healthcare where one would not have expected OR to show up, but it does. So you want to shoot at a tumor using various radiation beams, and you want to shoot at the tumor but without burning some important organs in your body. How do you do it? Well, you can adjust very finely the intensities of all the different beamlets so as to do it in the best way. And that turned out to be a mathematical programming problem. It's usually solved using linear programming these days. Now, what if you don't know where exactly the tumor is sitting, but it might be moving? Well, then what a doctor would do would be draw a big circle around the tumor and say, burn that whole thing. Well, that's maybe a little too much. So if you know a little bit about how it might be moving, you might use that information. You still have uncertainty, and then use robust optimization to be sure that you're covering it as it's moving, but you're not overkilling it. And that was Tim's PhD. And how this work, a different variation on this kind of theme, is a work of a current student together with David Kraft, another ORC alum, and collaboration with MGH, where the idea is as follows. You don't radiate a tumor just once. You do it over a sequence of, let's say, 30 treatments. And on some days, the configuration is good. That is, a sensitive organ is far from the tumor, so you can burn a lot the tumor without damaging the organ, and some days are bad where you want to be a little more sensitive. So obviously you should do something different on the good days and the bad days. Now, knowing that today is a moderate day, but anticipating that there will be some good days down the line, I should use that information to make an intelligent decision now. So what is this? dynamic programming, of course. Now, the real problems are huge and difficult, so that takes us to approximate dynamic programming. And so here's an application domain that some years ago I hadn't crossed my mind at all that there was room for OR techniques in such a context. So now let's move to a somewhat different theme that has showed up. And this is what we would call the value flexibility. This is a sort of interesting and old idea. One of the first places where it was introduced was by this guy. Does anyone recognize him? So the idea in soccer is that you have the defenders in sort of fixed positions, and there was the brilliant idea of having a libero or sweeper who basically takes up the slack wherever that's needed. And okay, so it was a great idea. Germany made great use of it, and of course OR couldn't be behind. Now, what's the issue here? Okay, it's good to have a great sweeper who's flexible, but people like Beckenbauer, there's not too many of them out there, and they're not cheap. So perhaps you need only a few flexible resources to take the slack and not too many. And something that was realized was that having just a little bit of flexibility actually can do a very good job. This theme shows up today in issues like data centers and call centers. For example, you have people who speak Spanish, people who speak English, but maybe some people in the call center who can serve both Spanish and English speakers. Taking that theme, a student has done some very good work where there's an abstraction of such a situation, where you have several streams of jobs that are coming. And dedicated servers. But then there's also a server who's more flexible, has a small fraction of the overall service resources of the system, but can go and serve wherever it sees a large queue. And it turns out that with just a tiny fraction of the overall resources, if they're allocated to the big server, this gives you a huge performance improvement. I guess the blue would be the one where you don't have any flexibility. The red line would be what you get with a tiny amount of flexibility. So this is work that's it's not a direct application in any sense, but it's an abstraction of situations that appear in some generic ways and which also call for interesting mathematics. So part of the work that is done in the engineering school, some of it addresses applications directly, but some tries to abstract and get to ideas that will have perhaps more general use and relevance in contexts that we do not anticipate today. And we always love to also look at puzzles and difficult problems. Bigger picture here is that a lot of what's happening these days is to understand how things scale. When systems become large, when you have lots of nodes, what is going to happen? And you have usually in complex systems sort of complex interactions. And there's some paradigm problems in queuing theory and stochastic modeling that have that kind of flavor. A famous one has to do with switch scheduling, where at any point in a switch you choose a matching between inputs and outputs, and you want to choose them in an intelligent way so that the overall delay at the inputs of the switch are not too big. So there's ongoing work along this. There are sort of big conjectures, very difficult and interesting mathematical problems. Our student, Wong, you probably saw his panel earlier today. He's done some very good work on this topic. So I just limit myself to these vignettes instead of trying to say about the big goals of any particular sub-area, but it's more to give the flavor of the type of work that's being done. Some driven by applications, some motivated by applications, some possibly inspired just by its mathematical content. Thank you.
Thank you. Our third speaker is Professor Dick Larson.
Good afternoon, everyone. Good afternoon. Okay, now I'm supposed to press 1. Press 1. Okay, now we'll test the sound. Nope. Try it again. You hear that little beep? Okay. So we should, those very nice gentlemen who set this up said he was so surprised. He thought us business people were PCs. And we're all Macs here. So it just shows that ORC people think different. Because we're all Macs. Ha 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 ha. Okay. So here we go. So I am now in ESD, Engineering Systems Division. This is the 4th academic department I've been in my multi-decade career at MIT, EECS, DUSP, CEE, and now ESD. ESD is a new invention for many of you. It's an interdisciplinary, interdepartmental creation. And interestingly and figuratively, literally, it lives right above the OR Center in E40, right across the way. So ESD likes to look at problems at the Venn diagram intersection of traditional engineering, here viewed as OR, let's say, social science, and the management sciences. ESD, most ESD faculty, there are ESD faculty, unlike the OR Center, but most ESD faculty are either dual or joint appointments. Dual means that their tenure track records are 50% in ESD and 50% in an academic department, mostly in the School of Engineering, but not exclusively. Whereas a joint appointment is you have a home department somewhere and then a joint courtesy department elsewhere. These joint and dual appointments span all 5 schools of MIT. Not just the engineering school, but all 5 schools of MIT. And basically, what ESD people do in terms of research is driven by the contextual domain of the research, usually reflecting the Venn diagram intersection of those 3 things. So it's not driven by methodology per se, but sometimes methodology surfaces as a result of trying to look at those kinds of problems. Now, I sent out an email to the ESD faculty and asked them if they'd like to contribute to this talk. And I'm showing the slides that I got back. There are about at least 10, if not more, ESD faculty members who are affiliated with the ORC. I only got back contributions from 3 of them. So one of them is Chris McGee, who I think now is in Singapore. He's 6 months in Singapore and 6 months here, something like this. Oh, he's back at MIT now? I'm on sabbatical, so I wouldn't know that. Okay. And this gives you an example. Things in social networks, complexity, IEE transactions on management, and you can read those kinds of things. He says, well, if you have a broader definition of OR, you get into International Journal of Engineering Education, technological forecasting and social change. These are the kinds of things. Chris has been very productive since he's joined the MIT faculty, and these are the kinds of things he and his colleagues and co-authors are dealing with. Here we have Ali Dweck, who until recently was the co-director or the assistant director of ESD. And like a number of ESD-related faculty, they're applying quantitative techniques to look at engineering designs of complex systems, particularly systems as they evolve over time. You might have to change the 13th component or the 33rd component, but that change reverberates throughout the entire system and requires changes in maybe 15 other components. So they're looking at that and looking at how to sequence things to minimize that kind of complexity. You have a similar kind of issue with Jessica Transick, who is a new assistant professor in ESD. She's full-time ESD, not a dual appointment. And she's looking at some similar things with design of complexity and technology improvement. So those are some of the examples. Now, at the risk of doing something which I've had something to do with, but also others, Professor Dan Fry, Mechanical Engineering at ESD, Professor Eric Klopfer, who's ESD's newest joint appointment. He's from Department of Urban Studies and Planning, and now at ESD. Well, the idea is OR in high schools. Ken Chelst is doing something like this. He's been doing it with NSF support with North Carolina for about 2 or 3 years now. And so basically, let's give you an example of what I'm talking about. I would call this a random incident that occurred on campus. You recognize Arnie. Anna Tatelman is a current ORC doctoral student.
Hey, Arnie.
Hi, Anna. What's in the big bag?
Plenty of trouble for me.
Oh?
My school had 2 performances this weekend, and now I have to count all the tickets to see how many people actually went to see the play.
No, you don't. Here's an easy way of getting the answer. Pick someone at random who attended one of the shows, ask him how many were in his show. Whatever answer he gives you, just double it, and that's the answer. You don't have to count one by one.
No, I don't know, Arnie. I guess your method would work sometimes. But first of all, how would that person even know how many people went to see his show?
Anna, this is MIT. Don't you assume that that person would know exactly how many seats there are in the theater and exactly what percentage were filled? So let's assume he'll give the right answer, and then you just double it, and you're done.
I don't know. Even if that person knew exactly how many people were in his theater, I still don't think you can just take his answer and double it to get the exact number of people who went to both shows. You know, there's a saying, if something seems too good to be true, it probably is. Well, your rule is way too easy. I think it's too good to be true.
Nonsense. If my rule is not correct, I'll suck a lemon dry. There's no need to make complicated that which is easy. There's no reason you have to count the tickets one by one.
So Arnie thinks that what we could do to find out the total number of people who went to see both shows is to ask one person at random from either of the two shows and get his number of the people in his theater, double it, and we'll get the total number of people who went to see both of the shows. Do you think this method works? Are there some cases in which Arnie's method actually works every time? And are there other cases in which Arnie's method is bound to fail? We'll be back in just a few minutes after you've thought about it, and Arnie is going to have a lemon with him just in case.
Okay, there's an example of a ORC PhD student meeting one of our faculty on campus, and you can see which is the smarter of the two here. By the way, in scene 2, which I'm not going to show today due to time constraints, Arnie sucks a lemon dry. So this is an example of where we're looking at education as a complex system. I think if there were a mutual fund on education, and I don't just mean monetarily, but otherwise, that you could invest in with a 20-year return, education was where I put most of it right now, because that is something that's really taking off. Cindy mentioned the education innovations in the School of Engineering, and you read every day in the press about the STEM pipeline. STEM, science, technology, engineering, and math, K-12, K-16, K-PhD, the STEM pipeline, and that there's leakage in this pipeline. People who have the talents to have an engineering and OR science degree don't. Somewhere along the line, they fall out of the STEM pipeline, and once you fall out, it's very, very hard to get back. So we're looking at it. We have 2 research projects on this. I'm not going to talk about those today, but the example you just saw of the video is we're creating videos for high school math and science classes. In fact, I just showed this one yesterday in Washington, D.C., before 40 math teachers in the Washington, D.C. public school system for high schools. And some of them are going to actually see Arnie and Anna in the D.C. school system. So what we want to do here is get away from teaching to a test, rewarding rote memorization. We want the students to understand that if they're going to go out in the world and be STEM competent, they have to do what we do with you when you were students here. Look at a blank piece of paper. Basically, your job was to fill up that blank piece of paper with an approach to a problem that you hadn't seen before, not just plug into some kind of computer routines or Excel spreadsheet to get answers. Some of you might have actually experienced a doctoral exam question I gave at the ORC a few years ago. You pass a jogger jogging along. What's the probability you pass her again on your current jog? I won't go through all the assumptions, but this is the kind of thing. In fact, this one requires a deep understanding of random incidents to answer correctly. So the video you saw is an example of this project we call Blossoms. This is not a research project. This is the 3rd thing we're doing, which is actually implementation in the US and in partner countries. We're creating open education resources videos for high school math and science classes and engineering classes. And we have Walter Lewin, who's the rock star of physics, as one of our teachers, and we have many more, and some from partner countries. There's Pervez Hoodboy, a PhD graduate in physics of MIT, now Pakistan's most famous physics professor, teacher, and he has done one of these. We also have contributions from Jordan, Lebanon, Saudi Arabia, and Singapore. So not on rote memorization, but on developing critical and creative thinking skills. I think that OR is the thing to bring into high school math classes to keep these young people excited about math. Because the teachers who teach them don't know about OR. And they don't know about the wide applications that OR can give them and to motivate them to keep in the STEM pipeline. And the thing about this particular pedagogical model is it's a teaching duet. The teacher's still in charge of her class or his class. Students are sitting in the regular classroom, computers off, cell phones off, and they're watching these interactive short video segments, like this one. Karima is an ORC PhD student who's now graduated and works for Bill Gates in Seattle, fighting malaria in sub-Saharan Africa using OR methods and models.
Hello, and welcome everyone. My name is Karima Nigmatulina, and I'm a doctoral student at the Massachusetts Institute of Technology in Cambridge, Massachusetts. I'm excited to tell you today about a branch of mathematics called graph theory. You probably haven't heard about it before because it's not really algebra, and it's not really geometry, and it's not really arithmetic. It's something completely different. But it has many, many applications and is very useful, so I hope you enjoy the lesson. Let's start back in the beginning where graph theory was born. We have to take ourselves back to the 1700s to the city of Königsberg. Königsberg was a wealthy trading city in Prussia. And you can see on your screen right now a map of the city of Königsberg from that time. Königsberg was divided into 4 parts by a river called Pregel. The top part of the city was called Altstadt. The middle island part of the city was called Knapphof. The lower part of the city was called Vorstadt. And the right middle part of the city was called Lomsey. These 4 city parts were connected by 7 bridges. And the bridges are shown in red on the diagram that you can see here right now. So here is what the city of Königsberg looked like in the 1700s. So the citizens of the city really enjoyed their city, and they would walk around the city a lot. And they created a game for themselves. The game was, could they start in one part of the city, walk around in such a way that they cross all the bridges exactly once, not more, not less, and come back to that original spot where they started. So the citizens of Königsberg weren't able to come up with such a route, but they didn't know if they just couldn't do it or if such a route didn't exist. And this is the problem that we're going to start with today. Do you think that such a route exists? Can we start in one point of the city, walk around, cross all the bridges exactly once, and come back to that original starting point? Take some time with your teacher, see if you can come up with such a route, and if you think that you can, or if you think that you can't, please let me know, and you'll tell me in 5 minutes. See you soon.
The City of Lowell High School called us about 1.5 years, 2 years ago, said they use this now for juniors in their college math class to introduce them to discrete mathematics, because the introduction to discrete mathematics they'd used before put all the students to sleep, whereas this got them energized. First of all, there's a teacher's guide at the end of this, a video teacher's guide, and what Karima suggests that the high school teacher do is divide the class into 4 groups and give each group a printout of the map. These are downloadable as PDF files, and assign each group to be representative of one of the 4 landmasses of the city of Königsberg, and say the group that solves this first is going to get dinner at the restaurant of their choice on me whenever they want it. Big prize. Well, you know that there is no feasible solution to this, so there's no risk in awarding that prize. But at the end of the 10 minutes when they're trying this, you got the students exactly where you want them. They know exactly what the problem definition is. They're frustrated. They're competitive. They haven't won. And that's when she starts introducing graph theory with nodes, arcs, degreeness, directedness, all that kind of stuff. Ends up teaching them at a certain level, at an appropriate level, the Chinese postman problem. The idea there, again, is you're bringing high school students who are in math, wondering what relevance is this to me, and say, wow, even the mailman who delivers my mail every day, that's an interesting mathematical problem I wouldn't have known about, and it's relatively recent. So that's it. I know I probably run out of time. Have I run out of time? Do I have 1 more minute?
Yes.
I have 1 more minute. Okay, with 1 more minute, we'll do this. Arlington High School, Massachusetts.
This is going to be exploring the probability that 3 sticks made out of this one long stick, we'll call that unit 1 if you will. If you break it at 2 random points, what's the probability that the 3 sticks will form a triangle? And then we'll move on to seeing the video that was made by one of my colleagues at MIT. The program is called Blossoms. Now notice, this can be done in a very poor region. You can ship the video via computer anywhere in the world instantly with virtually no expense.
My name is Dick Larson, and I'm a teacher at MIT here in Cambridge, Massachusetts, USA. I hope you're feeling fine today and full of energy.
Are you?
We have an interesting challenge problem for you that's going to build in the math skills that your teacher and you have been working on these past few weeks and maybe months. Today's problem deals with triangles.
Okay,
And
I'm
if
going to
you're
cut that
currently in
guy
a
off, because
geometry
you've all
class
seen
in
that
high
problem
school-
before.
But anyway, that's what happened. This short video segment shows what happens in an actual high school. Now, we also have undergraduates, particularly who are in the Sloan School program, who are really studying OR. And one of them, Diana Monte, who came to us courtesy Jim Orland and Arnie Barnett, actually worked for us as a Year Up this summer.
Hi, my name is Diana Monte, and I'm studying economics and management here at the Massachusetts
doesn't say
Institute
OR,
of Technology in Cambridge, Massachusetts. Every great inventor is constantly aware of and questioning what's going on around them. This constant observation allows them to recognize all the potential for innovation
When I
that
first
the
saw
world
this,
has
I
to
said, I
offer.
wish she'd keep her eyes on
Today,
the road.
I'm going to challenge
going down
you
Memorial Drive,
to look
looking
at
in the
world
camera.
with a fresh perspective for innovation. Let's see all the opportunities for innovation that we can find driving around Cambridge, the home of MIT. Whoa, that was a close call. Did you see how that car nearly backed into me? I'm going to take a second and catch my breath while this car continues to back out. We're going to pause this video, but in the meantime, I have a question for you first. What does that near accident have to do with inventiveness? Talk with your teacher, talk with your classmates, and I'll be back soon to continue our discussion.
Okay, that's a sample of what we're doing, but we're trying to get, if you look at education as a complex system, and you want to get OR more widely known, let's expose high school math students to OR. Because even if they don't major in OR, get degrees in OR, they're going to end up working at Ford Motor Company or consulting companies or Procter & Gamble or whatever, and they'll know what the role of OR is in mathematics in the real world. So thank you very much.
Thanks, Dick. I just want to see how much time I have. So I want to thank the 3 panelists, Dick and John and Cindy, for their remarks. And originally I wasn't going to do this, but I thought I would talk a little bit about what's going on in OR at the Sloan end of campus. So for just a few minutes. And then I want to open things up. Hopefully you're bubbling or developing some good questions for discussion. And think about them and just give me a couple of minutes just to say a few words about what's happening with OR at Sloan. So several of the OR Center students formulated some questions about OR at MIT, and there were several of them that were about Sloan in particular that I thought I would try and discuss. They asked for OR trends in OR education at MIT, and I think Dick and others have spoken about that already. I'll raise a legitimate concern I have, which is, and maybe a measure of success of what we do. Right? As I look around campus, and I don't have statistics on this, but my sense is that there's a proliferation of optimization courses, probability courses, machine learning courses in a lot of different departments at MIT. And, we can view that, again, as a sign of success, but it's this sort of diffusion makes it harder to sort of pin down what's OR and what's not OR, all right? And also at a certain level, it just seems with every coming decade, computer science takes over another field. And so my guess is in about 20 years from now, they'll even take over, Slovakian languages or something like that. So, but I do see computer science, a lot of what we used to call theoretical computer science doing a lot of OR. And again, optimization, stochastic systems, computational statistics, machine learning, things like that. Another question that was asked was, what are the past and future trends in operations research and operations management? So my sort of 2 or 3 sentence version of an answer to that is as follows. I would say when I came to MIT, which was around a quarter of a century ago, operations research and operations management, they seemed to, at least at MIT, sort of, there was a lot of interaction, a lot of cross-fertilization going on. And then with all of the emphasis on U.S. manufacturing and the need for stuff that is specifically oriented towards manufacturing and having sort of, I think there was a sense, perhaps people were looking at me as a bad example thereof, that sort of pure OR people think of manufacturing as, consider a plant P that makes a product Q or something like that, using people M or something like that. And so it seemed for a while OR and OM kind of went their separate ways. I mean, there was peaceful coexistence, but there wasn't a lot of cross-fertilization. But I would say the last decade or so, they seem to be coming back together. In particular, I would say as traditional OM is also embracing sort of services and things like revenue management and supply chain and contracts and all sorts of stuff that I pretend to know a lot about, but actually don't. But that is my sense of that OR and OM were kind of close, kept them apart, now are coming back together. And I don't know what the future holds, but my sense is that they'll be coming even closer together. Another question that was raised was about operations research and MBA education. And so here it's a bit of a puzzle to me, to tell you the truth, because I can tell you what's going on in MBA education and operations research at Sloan and MIT, but I suspect it's not the story nationwide. Okay, so and the story nationwide is not as pleasant as the story I'm about to tell you, which is for a variety of reasons, and I can't quite explain them, but I have several hypotheses. I would say operations research is enjoying a healthy resurgence in the core of our MBA curricula at Sloan. And it's really nice and it's fun and exciting, especially for our group at Sloan. It's exhausting at times, mind you, as well, but it's very good. And that, just to give you an example, that we have 2 mid-career degree programs. One is called the Sloan Fellows Program, which is a full-time mid-career program. And then we also have a mid-career, what's called the Executive MBA program, which is people do it on weekends, like every second or third weekend over the course of, I think it's 2 years. Okay, so those 2 programs, well, one is brand new, and the other has been sort of reincarnated. Okay, and both sort of came to the OR group, the program designers, and said, "We want your material in our core." Okay, and part of me thought this was great, and part of me thought, we've got to be able to deliver to people mid-career, okay, who have tons of experience and are already, at the higher levels of their organizations. And the track record so far over the last year and a half has been enormous success. And Dimitri Bertsimas' story this morning that in the executive MBA program, the students actually vote for which electives that they want the school to offer on the weekends as part of the elective piece of the program. And the students voted they wanted corporate strategy and they wanted another OR course. And so that was, to me, impressive. And now we've got to deliver it, and I'm very confident that we will. So I don't, tell you the truth, I'm a little pained because I don't hear these kind of success stories so much at other schools. And it begs the question, okay, so what are we doing so well here? Or is this just good luck? Okay, and there might be a component of luck, but I think one piece of it is simply is good teaching, that we work hard to develop good curriculum that all our faculty can deliver well, so that's a piece of it. And is this a little self-serving? Well, I'm one of those teachers. I think we do a good job. Okay, so I'll just leave it at that. But also, I think those of us that are on the faculty here, we're not apologists for OR. We don't go, well, I know you don't really want to learn this, but I think it's kind of interesting. We don't do any of that because we know the great value of it. We know the value to all of these companies, and we either in the past or present have done a lot of applied OR ourselves, and so we speak with confidence and knowledge. And I think that and good exposition is my explanation, I would say, for our current success. I hope it continues. All right, and I can't adequately address what goes on at other schools. So with that, I invite questions from anyone on any aspect of what we've been discussing up here. Deverett. There's mics. Yeah.
Well, those excellent sets of presentations, and I really felt energized now. So here is a clear situation that OR as it is, and it's clear from presentation and from many of our experiences that it's been across the boundaries, and it has clearly lots of virtues. And possibly you could look at another disciplines where they're very gated, and that could have also lots of virtues. And I would just like to ask, as a panelist's opinion, maybe opinions of others, are there virtues of changing this, the way this OR is? I'm not saying that we could, but that's a question.
I invite any of you all.
Well, I think that the MIT model has worked extremely well. It has made the presence of OR to have such a very large critical mass, continuous presence, vitality, new topics coming in as the times demanded. And that's basically due to the fact that instead of being one gated department, it's a loose association of people who can come in and go. So I think that we have hit on a good model.
The issue of these porous boundaries has been a topic of the OR profession for at least 3 decades. It was partially behind the merger of TIMS and ORSA in the 90s. And when I became president of Informs, we had a $1 million plus budget for OR, the science of better. People made all kinds of jokes, OR, the science of butter, OR, the science of batter, but we spent $1 million on that. I don't think it was well spent. I think it was squandered, kind of like, some kind of cash for clunkers kind of program. But so this success has been an issue all along. People have tried to rename the profession. Even the NAE portion that has OR in it tries to rename itself every 5 years, so far unsuccessfully. So I think we should celebrate the success and not worry so much about the name.
Other comments on that?
I'll just make the comment that what I've seen lately is, this trend towards the disciplinary boundaries are just kind of dissolving away. And more educational programs are crossing boundaries. And at MIT, we, the ORC, sit in a really interesting place because I think we've gotten a lot of attention because for decades we've been doing this cross-unit education, and others are looking at us as proof of concept that it can be done and sustained, and looking to how we did it.
I'll just make one comment about it. I think it's been a risky strategy that has succeeded so far, and the risks, and I think it's great, and I hope it continues, right? Because I think think of MIT creating an OR department, okay? Then all of a sudden, all these people from other departments sort of think, well, if I really want to interact with those people, I'm not from their department, that I don't know if my department will let me guest lecture in their courses so much, et cetera. But the risks are that with the current strategy, and some of you know this as students, right, is that the center doesn't control its faculty, and it doesn't control its courses. And hence, it has only limited control over its curricula, okay? And so we've always been able to manage through that, okay? And I hope we will continue to be able to manage through that. But it's not without its stresses at times. Lincoln.
Thanks. Just to piggyback on that, I actually, one of the things I really enjoyed about being in the OR Center was the interdisciplinary approach. The idea that we could sit around the lunch table and, you know, I'd be working on something education related and someone else would be doing something in the medical field. And I really thought that exchange of ideas was a real strength of the way the center is organized. I had a couple of questions. One was regarding Blossoms. You know, I remember working on guided learning pathways many moons ago, but this is really exciting. And I was just curious, is there either anecdotal or is there plans to just kind of measure the impact or the stickiness of the Blossoms approach versus what you're saying? And then just a second question just regarding the mid-career folks being drawn towards OR. I'm just curious as to see what sort of diversity you're seeing in that group.
Two questions for two different people?
Yeah.
Yeah. Regarding Blossoms, we just finished the third year of the project. Our focus has been on production, and production from not only here at MIT, but our partner countries. And so Washington, D.C. and the state of Florida, this academic year, are our two working laboratories where we're actually going to try to train and motivate the teachers, hold contests for the teachers that they themselves can design and build Blossoms modules, have them each do at least 2 of them in their classrooms, and report back to us on evaluation forums about how it worked, what's wrong, what's right, that sort of thing. So hopefully by May or June of next year, we'll have evaluation reports from both Washington, D.C. public school system and parts of the state of Florida.
Thanks, Dick. So, Dimitri, I think I'll ask you perhaps to respond to Lincoln's question about the diversity in the executive MBA program.
So there was diversity across gender, about, I would say, almost 50-50 men and women. There was diversity along industries. We had internet entrepreneurs. There were high executives from financial firms, from marketing firms, from biotech firms. It was very, very diverse. I mean, I could not say what unified all of them. What the key characteristic that I had that I could say was that they were high-achieving people who at the same time were managing a company, a family, and taking very hard homeworks at MIT. That's the only thing I could say that united them. But it was a very, very diverse environment. I don't know if it answers what you asked me.
Oh, yeah.
Thank you, Dimitri. Mitchell.
Okay, so I've been blamed for putting a downer on this morning's program by Eddie, but I figure this is a more uplifting question. If I have conversations with Dimitri or listen to what any of you are saying, it paints an extremely bright picture of the future for OR, and I believe in that. I think there really is a bright picture. But one of the things that I saw was the constraint or the bottleneck for this were things like funding, available faculty, and if you really believe in the future of what I think we're going to be seeing happen over the next 5 years, the demand for this type of education is going to skyrocket. And I'm just wondering, since the topic is OR at MIT, how are you planning for that? What are you thinking about? I mean, how does that fit into your sort of plan for what's going to happen at MIT with that? Because I think you are the best place for doing this sort of stuff.
Okay.
More uplifting.
Yeah. So I'll any of the panelists want to answer this, or perhaps one of the two co-directors in terms of educational response.
Trial co-directors all over the place.
Right, no, but we're planning for the future. No, but we're not. We're the past. So,
I can make one comment, and then I think that it would be good for these guys to say something about what they're doing. But you're absolutely right that this resourcing of these kinds of programs is, and Rob said this too, this is the tricky part. I mean, in some ways it's pretty remarkable that the ORC has been around and has been so successful when you look at the model of how things are funded. So one of the things that we're doing, you know, the project I showed you with the graph, a similar parallel project is to look at the degree of contribution to different educational programs by faculty in a department, because that's where faculty are, right? They're owned by departments. The idea is, as we understand how much faculty and CEE contribute to the ORC degree programs and how much faculty and EEC, et cetera, we can begin to get a better understanding of how resource flows maybe should work. Because right now, our metrics are, if we have any, they're based on departments. And it's clear that model isn't up to date because so much is happening across departmental models.
So when I was 23 years old, when I finished the mechanical engineering department and came to MIT, I was uncertain about what I would do. I actually came to the mathematics department because I liked mathematics, and I did not know about the existence of the center at the time. And during my first semester, I learned this place, Operation Research Center. I knew something about OR in the past, and I was interested, excited about it, then associate my career with OR. So obviously I was very positive. Now it's a period of, at least in my lifespan as a scientist in the area, that I'm perhaps the most excited. Now, if there's a point in time where I think our time has come, I think this is the time. I mean, the way I would position it is that if you play a game of poker, there are a few times just to go all in. This is the time, in my view. So the way where I would position the place for the future, I would position it in the area of analytics. I truly believe that in the next 5 to 10 years, analytics will be of the same strength as or visibility as the personal computer was in the 60s and the 70s. Other examples that I would pose on that, I read The Economist every Saturday, and every single week in the last couple of weeks, I see a full page of major companies, SAS, IBM, HP, with analytics in the title. So I don't know if you've seen them, but I find them very impressive. So therefore, what are we doing in terms of that? I think we should, I mean, from my perspective, I know we have been discussing for some time. I think the time has come to act we have historically an exceptionally strong PhD program, which is admittedly one of the best in the world, a very strong but very small master's program. I think the time has come to make the master's program at the same level as the PhD program and potentially more. We discussed this in the morning. That's one direction. And the other direction is potentially, although we haven't discussed it extensively, is to think of our influence in the undergraduate program. I think there is huge demand at MIT about, I mean, after all, these are very smart kids, 18, 19, 20 years old, that are very strong mathematically. They don't know about our field very well, so that might be another opportunity as well. The center is not equipped well to accommodate this. We don't have central control of courses. We don't have, but it's definitely a lot of discussion that we have been discussing for some time about what to do. I think pointing into I mean, this is a personal perspective. This is not something that it's an official, although we have been looking into a master's program. So focus in analytics with a master's program and potentially looking into undergraduate down the road. That would be my sense.
Thank you, Dimitri.
Yeah, I think we have exactly the same perspective, except that I don't really care about names, analytics, or OR and all that. But I think one thing that we look at when we discuss and respond to this question is indeed what should we do. So one is indeed the master, and I think we are far ahead on that. And so the idea is a one-year program without thesis. It's probably going to be called analytics. So that's one aspect. The involvement with the undergraduate is another one. But when we look at it also, we would like to have the participation in the schools that have been supporting the center more or less by providing faculty to be even stronger. So right now, in terms of the administrative unit called the ORC, we would like to have Sloan and the School of Engineering to be more involved. For the following reason, if you really want to go from a size of a doctoral program that we have and double the size, we are really getting to a point where we need to have not necessarily control, but at least access to some resources that are needed. And so that's another aspect of it. So looking at the education aspect at the master level and the grad, and then the administrative unit, not necessarily becoming a department. We don't want to be a department, but really getting the two schools more involved. And this is a little bit tricky. I mean, we don't want to have 10,000 different reporting structure, but we need to have some support there. So essentially that's that. And what we have been doing also is really getting more and more faculty involved with the ORC and new faculty coming. And so when you look at the new hire within mechanical engineering or EECS or economics, we look at folks that actually do OR, even though they don't call themselves OR. We get them involved, and if there is a fit there, then we get them involved. So by doing that, so that's the perspective of the faculty and ORC. I must say also that within the existing ORC students, we have a bunch of very entrepreneurial students, and they want to they recognize the need to get our undergraduate at MIT involved with the ORC by organizing some competition and things like that. One thing that we realize is that if you look at the application to the ORC in the doctoral program, we do have quite a bit of folks that come from math background, but almost no applicants from MIT. Our undergraduate students don't even know about the ORC in some sense. And so we are trying to get them more involved because some of them are clearly of the caliber that we would like to have. Okay, that's all what I wanted to add.
Thank you, Patrick. Other questions? I see Charlie Marge.
That's right, Charlie Marge, class of '86. Picking up on that theme, and probably mostly a question for Dick here. In terms of exposure to OR and the education issue, when I was an undergraduate here, my exposure to OR came by taking Professor Little's class, an introduction to OR, as a sophomore. And I was absolutely enamored with it, and I wanted to do it, and yet there really was no other opportunity after that. I was basically told, to wait 2 years until I could be a grad student and then study OR. Fortunately, I got involved in one of Jim Orland's Europe projects and was able to at least stay interested in the field while I was working on my math degree. So I have two questions. One is around this issue of how do we get the undergraduates involved, because it was basically, yeah, it's a great field, but you can't study it till you're a master's student. At least 25 years ago, that was the answer. But then on this issue, the question for Dick about high school education, I was absolutely shocked when I found out that my oldest son, who was in his first year of high school, 9th grade last year, actually learned something about linear programming as a part of the curriculum in Lexington. And I couldn't believe it because, again, given my experience, I didn't even know anything about this till my sophomore year, and then told to wait until I was a grad student to really get into this. I was wondering, Dick, if you could kind of comment on that development in terms of at least some high school students somewhere learning about linear programming, their curriculum, and how that might tie in with some of the stuff that you're doing. So those are two different questions, one about the undergrads and then one about the high school.
Which one do you want to do first?
I mean, I'll take a stab. I mean, I really don't know what to say about the undergrad. I mean, you're asking, well, let me just ask, does anyone on the panel?
There's a management science major.
So, yeah, actually, I'll invite another former co-director, Jim Orland, maybe, to answer this question. I can.
Yeah, and my thesis advisor, by the way.
He's got that mic.
Thank you, Rob, and thank you, Charlie. He's my first thesis student, actually. So in terms of undergrads, we actually do have an undergrad concentration in operations research, recently renamed the concentration in business analytics and operations research. The major reason for that is I figured that when people list it on their resume, it's really nice for the people who are recruiting here to actually have some clue what they did. And the recruiters aren't recruiting undergrads in operations research per se. They're just looking for very bright undergrads. So business analytics helps out. I think we could probably increase the number of concentrators in OR. I think it would be great if we had an undergraduate class that was stochastic modeling, and I'd be happy to talk about that. I'd be happy to talk with the OR Center about getting people involved, because the concentrators are a natural one. Inside the concentrators in OR, they're majoring in management science, so they already have a number of OR classes. They're already taking optimization, probability, statistics, and they also have background in micro and macroeconomics and computer programming. So that's a starting point, and then they take an additional 3 courses in operations research. So that's about it.
Thanks, Jim. Jack.
Diana Monte, who made that last Blossom's video, almost having a car accident, was a student of Jim Orland's, and I think you might agree with me, Jim, by the time she's a graduating senior, she might have taken most of the doctoral program courses in OR. She's really on a trajectory to do that. She's very self-directed and very much involved with OR, but you have to seek these, the undergraduate has to seek this out. We don't really go and market to them.
Oh, I left out, and I'm not going to go for the mic, but we have an undergraduate management science minor, which has gotten very popular. It's actually currently the second most popular minor at MIT. And I think that that's a good, I think so. It's more popular than the management minor. And I think that that's a good way to attract students or tell students about operations research. And it's very popular within the math department. So I think the mathematicians in particular are going to start learning about operations research much more commonly.
With regard to Lexington High School, did you know that the admissions department here at MIT views it as probably the best taxpayer-paid private high school in the country? So
that explains my tax bill.
Having had 3 of my own children graduate from there, I'm familiar with the fact that they introduced linear programming to either at the freshman or sophomore level. My famous broken stick problem that I've probably did for many of you, I've actually done 3 times for sophomores taking geometry in the Lexington High School system. On the 3rd and final time, the saw slipped and I seriously cut my index finger on my left hand. And a student, a female student, came up from the 2nd row, and she had a first aid kit in her purse, healed it all back together, and we finished the whole class. I went to graduation that 2 years later, 3 years later. She came up to me and she says, Professor Larson, the one class I remember most in my 4 years at Lexington High School was this one. And I don't know if I felt good about that or not. But anyway, having been just in Washington, D.C. in the public school systems there, where I met an MIT graduate from mechanical engineering who's been now teaching there for 2 years, he said 90% of his time in his math classes, he loves teaching down there, is discipline of the students. So that's at the other end of the extreme of a Lexington High School type of, or Newton High School or Wellesley or all these others, Lincoln Sudbury, et cetera. So we have a wide dispersion of what's necessary. I have to say some of the things I showed them yesterday, they said, oh, is that what you think a student should be able to do when they become a freshman at college? And they were stunned that we're looking for that level of performance. So the country is very widely distributed on the quality of the high schools and what's going on in them and the students' attentiveness to these sorts of things. But I still think that OR, which shows the relevance of mathematics, let's say, and physics to some extent, to real-world operations can encourage can encourage people to study in this direction, the STEM area, and reduce the leakages that we have. But time will tell whether that's successful.
Right. I mean, I think it's all a question of inspiration. The reason I bring it up is because I was so inspired by Professor Little's class. You know, that, wow, this is great stuff. And of course, no one has more enthusiasm than Professor Little for operations research. We need to inspire kids at the high school level to know about this, get them excited about math so they're looking for more of it when they come here or at other colleges as well. And it's really exciting to know that you're involved here at MIT and trying to do something that's going to inspire high school students. So I think that's great.
Well, I think we're just about out of time, unless someone has a particularly burning question that they feel they must ask. Don't want to squash learning here, you know. Okay. So I guess we'll take a break then for 30 minutes. Yeah. Okay. Thank you to the panelists.